Hello dear friends, this is Dr. Diptesh Patel and I'll be teaching you jet propulsion and aircraft engineering. This is lecture number 2 of fundamentals of gas dynamics. Now, this is the outline of today's video session in which we are going to see stagnation conditions and its parameters of different situations. So, in this video lecture, we are going to cover stagnation pressure, stagnation temperature, stagnation sound velocity of sound, and stagnation density. So, since we have studied what is a stagnation state or what is stagnation condition in previous lecture, let me just give you remind you about which situation is called the stagnation condition. So, stagnation condition is the state when the fluid is deaccelerated isentropically to zero velocity and zero elevations, and that state is known as the stagnation state. Especially in gas dynamics, this state is known as or is referred as a reference state. So, let's settle up. Let's start with the stagnation temperature that you can see in the slide. So, first of all, what is the stagnation temperature? Since stagnation temperature is the temperature when the gas which is flowing in the line or which is flowing or which is fluid, considered as a fluid, is adiabatically deaccelerated to zero velocity at zero elevation, that is known as the stagnation temperature. So, it is basically a temperature when the gas is come to rest adiabatically to zero velocity or at zero elevation. Now, we need to find out how to find the stagnation temperature is. So, let us begin with the stagnation enthalpy. First of all, since we know stagnation enthalpy, since it was derived in previous lecture, HO, which is the stagnation enthalpy, that is equal to H plus 1 divided by 2 C square. So, that is the stagnation enthalpy in which we know HO is a stagnation enthalpy, H is a static enthalpy, while C is the velocity. Now, the stagnation enthalpy and the static enthalpy for a perfect gas can be derived as HO is equal to CPTO and H is equal to CPT. That we have studied in basic thermodynamics. So, since we know that HO is equal to CPTO and H is equal to CPT. Now, let us substitute these two values of stagnation enthalpy and static enthalpy. So, let us substitute these two values in above equation. So, if you replace these with HO and H, the whole equation would become CPTO, which is equal to CPT plus C square divided by 2. Now, let us divide the whole term with Cp. So, if you divide it by Cp throughout the equation, like on the both side, the equation would reduce to TO is equal to T plus C square divided by 2Cp, since we need to add the Cp underneath. So, the whole equation would reduce to TO is equal to T plus C square divided by 2Cp. Now, let us get the ratio of stagnation temperature to static temperature. Since we have derived already stagnation temperature, that was TO is equal to T plus C square divided by 2Cp. Now, let us find out the ratio between the stagnation temperature and static temperature. So, TO divided by T, that is the ratio of stagnation temperature to static temperature, is equal to 1 plus C square divided by 2Cp. So, TO is divided by 2 is equal to 1 plus C square divided by 2CPT. Now, since we know that Cp is equal to gamma R divided by gamma minus 1 and also A, which is considered as a sound velocity, A is equal to under root of gamma RT. Now, let us put these value in the equations called TO divided by T. So, that was the ratio of stagnation temperature to static temperature. So, let us put the values of Cp and A in this equation. So, the equation would become, let us say the equation would become TO divided by T is equal to 1 plus C square 2 gamma RT divided by gamma minus 1. So if you replace it with Cp, the equation would become TO divided by T is equal to 1 plus C square divided by 2 gamma RT divided by gamma minus 1. Now since we know that gamma RT, under root of gamma RT is equal to A, which is a sound velocity. So if you can change it over and you can replace the gamma RT with A square. So therefore the equation can be written as TO divided by T is equal to 1 plus gamma minus 1 divided by 2 into C square divided by A square. C square divided by A square. So here C is the object velocity and A is a sound velocity. Now this term can be replaced by Mach number, since we know that Mach number m is equal to C divided by A. It is a ratio of object velocity to the sound velocity. So we can replace the whole term by m square, and therefore we can write that equation is TO divided by T is equal to 1 plus gamma minus 1 divided by 2 into m square, where TO is a stagnation temperature, T is a static temperature, and m is a Mach number. Next one is a stagnation velocity of sound. Now stagnation velocity of sound is the velocity that obtained by deaccelerating gas at isentropically at zero velocity at zero elevation. And velocity of sound for perfect gas, since we know that A is equal to under root of gamma RT. So the velocity of sound for perfect gas can be write as AO is equal to under root of gamma RTO. Also R, characteristic gas constant, R is equal to gamma minus 1 upon gamma into Cp. So now let's put the values of R in the above equation. By substituting the value of R, we can find that AO is equal to under root of gamma minus 1 into Cp into Tu. So the whole term gamma would be divided, and therefore AO is equal to under root of gamma minus 1 into HO, since we know that the stagnation enthalpy HO is equal to Cp Tu. So AO is equal to under root of gamma minus 1 into HO, and that is the stagnation velocity of sound. Next one is a stagnation pressure. We can use the same definition by inducing the pressure. So stagnation pressure is the pressure of a fluid which is attained when it is deaccelerated to zero velocity at zero elevation in a isentropic process or in a reversible adiabatic process. So here let's find out the ratio of stagnation pressure to static pressure. Now that values can be derived by isentropic relation, since we know that the isentropic relation says P1 divided by P2 is equal to T1 divided by T2 raised to gamma upon gamma minus 1. So same equations can be used over here, and we know that PO divided by P is equal to TO divided by T raised to gamma upon gamma minus 1. Now TO divided by T, that is the ratio of stagnation temperature to static temperature, and that been already derived. So let's put their values, the values of TO to T over here, and we can get PO divided by P, that is the ratio of stagnation pressure to static pressure, is equal to 1 plus gamma minus 1 divided by 2 m square raised to gamma upon gamma minus 1, where PO is a stagnation pressure, P is a static pressure, and m is a Mach number. Last one is the stagnation density. Now stagnation density is the density of gas when it is isentropically deaccelerated to zero velocity at zero elevation. Now from isentropic relations we can write down rho O divided by rho is equal to PO divided by P raised to 1 upon gamma, since we have used the same kind of isentropic relations in previous slide. So P rho O divided by rho is equal to PO divided by P raised to 1 upon gamma. Now let's put the values of the ratio of stagnation pressure to static pressure in the above equation, and we can get PO divided by P is equal to 1 plus gamma minus 1 divided by 2 m square raised to gamma upon gamma minus 1. So therefore, the equation can be written as rho O divided by rho is equal to, inside the bracket, 1 plus gamma minus 1 divided by 2 m square raised to gamma divided by gamma minus 1 raised to 1 upon gamma. Now the whole equations can be reduced to rho O divided by rho is equal to 1 plus gamma minus 1 divided by 2 m square raised to 1 upon gamma minus 1, where the rho O is the stagnation density and rho is a static density. So in short, this is a ratio from stagnation density to static density. So this is all in this video section. If you have any doubt, you can write down in the comment box. Thank you very much.